The way this is going to run today through Wednesday at this time on this stage, we will have presenters. 4 today, 5 or 6 tomorrow, 4 on Wednesday. They present for about 10 minutes. Our august panel of judges asks them very hard-nosed questions, hold their feet to the fire, unleash the lions, whatever the other Roman metaphors are. And then they jot down their votes, and we go on to the next set of presenters. Wednesday at 5:15, once we're all done with that, we'll tally up all the numbers. Big day. We announce the winner. Let me introduce our judges, who, in one form or another, have run this show. First up is Mac McNamara. I think you were 2017. Rob Aiken, 2020. 2019. Wei-Lii, 2020. And Harry Foster, last year. Well, we came back partly virtual, partly live. Anyway, we're back all live now. We're going to kick off with our first presenter. This will be Tim Helvey from the Marvell team, and he's going to be presenting a billion instance timing sign-off. Tim, come on up for your punishment.
Yeah, I'm not sure what I did wrong to be first up here. I think my abstract, I forgot in my abstract. I didn't put the words ML and cloud in my abstract. That's why I'm up here first. So I'm presenting billion instance timing sign-off. My name is Tim Helvey from Marvell, and presenting on behalf of my colleague as well, David Lawson at Marvell. Starting with some background here, in our group at Marvell, we partner with our clients to help design their chips, and these chips have become bigger and bigger over the last 15 years. I plotted some data on the right, just some sample designs. The blue bars are sample designs, and the red is meant to estimate the cost of sign-off of those designs. And despite improvements in the hardware, faster processors, memory prices coming down, sign-off continues to get exponentially more expensive as well. So with that background and designs getting bigger, we need to break the billion instance design into manageable pieces. So I didn't have it in my abstract, but I'll correct it. Machine learning and cloud computing fixed all of our problems. Just kidding. We do use cloud for our some of our timing analysis, and machine learning just makes it worse because some of our biggest designs are coming from the machine learning space. Very, very large designs represented there. I'll present 2 possible approaches, not the only approaches we could take, but 2 leading approaches on how to handle the large design data that we have. So distributed or hierarchical. In the distributed approach, the tools will auto-partition the design over multiple clients. Sort of looks like a single session running on many machines. In the hierarchical approach, we'll build up from smaller blocks, following the physical hierarchy, build it up with abstracts, and come up toward the top of the chip. Just looking at the day-to-day schedule as we approach the design with these techniques. In the distributed approach, we'll take day 1. We'll start off, there'll be several corners that we need to look at, so we'll start a bunch of runs in parallel, and then perhaps 2 or 3 days later, those giant runs have finished. In the hierarchical approach, day 1, we can time the lower level block, generate abstracts, possibly iterate on that. Those run fast enough. We may iterate on them a few times. Day 2, we'll time the parent with those abstracts and generate sort of a reverse abstract context for the children. And day 3, verify the children within those contexts. Just some comparison on the two. In the distributed approach, there's minimal data management for the user. Effectively only one session to monitor, although it's running on several hosts. Maybe faster overall turnaround. This is a better approach for final sign-off, where you don't have to iterate, you just want to have all your results as quickly as possible. It may take some investment to align your client configuration to the available machines. In the hierarchical approach, we enable iteration quickly at each level. If you need to do some timing ECOs, it's more efficient to iterate on those lower level blocks or iterate on the upper level blocks. Maybe lower cost because we don't require as many large footprint machines. Possibly better for timing closure, but it is some additional work to manage all of those parallel independent sessions, the data that they produce, puts a lot on the user. In both of these approaches, I will say in our practical usage, we've become conscious that 90% of all design, or 99% of all timing sessions are not using these approaches. So you can imagine that we may struggle with a little more instability when we're using features that 99% of sessions aren't testing. In conclusion, got to fly through here in 5 minutes. As leading edge designs continue to grow, sign-off cost continues to grow with it. Both of these approaches, the distributed and the hierarchical approach, have benefits. And these advanced approaches require some additional work, which needs to be planned and staffed by the timing team. Effectively, going back to that first chart I had showing the exponential growth in cost, that's not just machine cost, but the amount of time the timing team spends on managing, just being responsible for the runs completing and verifying the data. That as well is growing exponentially. The tools let us get the job done, but there's a lot of overhead with them on the large designs. That is my presentation.
Wow, very efficient. Nicely done. And is your co-author David Lawson with us in the audience?
He has family visiting that he needed to be home for today.
Okay, all right. Otherwise, we would have called him out. Harry, fire away.
This is a two-part question. One is, what do you really think of machine learning and cloud? And the other part, a more serious question, is what you didn't mention was what's the overhead in the partitioning?
Both good questions. And machine learning, I'll say I've been to DAC for several years, and I've found it fascinating over the past few years to see the progression where people come up and present sort of theoretical machine learning approaches. And I think just in the past, really I noticed a difference last year, and I'm looking forward to this year, where people are really using it for practical, low-level, average engineer jobs. We're seeing some of those machine learning techniques starting to gain traction at the low level. Partitioning, I'll just throw out some really rough numbers and say that might add 20% to the overhead of the run. We've seen it vary a lot based on the architectures and how well, what sort of overlap and just design-specific things can vary that a lot from block to block.
Other questions?
Yeah, so first I think the problem is definitely the real problem. I think that's a real challenge. So one angle you didn't mention, but I just wonder, like from your experience, the other part to tackle this is like incremental, right? You know, because you may have the design, you know, with the previous iterations or previous cycles, right? You know, there could be like small changes you did from the beginning, you know, like either customer give you a different small analysis change, right? then do you think is there any way we can reuse like some of those information for your next one, which may save some of the overhead costs or things?
What company do you work for?
Cadence.
Can you answer that one for me? Yes.
We can talk more offline.
I would love to see some more capability here. Ultimately, at the end, I think we have really, for that takedown, that is wonderful. I would love those techniques. At the end for sign-off, I think we have a really entrenched mindset that sign-off run has to look at the whole design, and we're kind of wary of any machine learning sort of techniques in the sign-off. And any sort of incremental approach, we really want to see the whole design from start. Good question, thank you.
How would your answers change, or would they change, if instead of a billion instance thing, it was a 10 billion instance thing?
You know, that's a good question, and I was thinking how to work that in where, like, when I wrote this abstract, I felt kind of good about, like, we're doing a billion instance design, and now already I feel like a billion, that's kind of just like table stakes to sit at the table, like everybody has a billion instance design now. I think really, I'm going to pick on Joao a little bit. I've talked to his people. They say, yeah, we can scale to as many clients as we want, but if I take this current architecture where I'm running 16 clients now and I need 160 clients to scale up on it, that's not going to work. So I think really we're going to have to embrace more of the hierarchical approaches that we're talking about, or some other techniques where we're not just doing the same thing, analyzing a full design flat across 160, 200 machines. That's a lot to ask for even in a cloud environment.
Yeah, I think if you had done 10 billion, then your presentation would start with T instead of B, and then you would have gone later in the day.
Yeah.
Was something to think of. But no, I think we're going to have to do hierarchical, right? I mean, there's just no way,
Yeah.
right? But it is a design change, so people have to be okay. You know, registers between the if you can track what the designer has some hierarchy in it, if you can do the timing, so it's really 10 big designs that are connected together at registered, maybe that can work, and let the recalcitrant folks accept that.
Yeah, agreed.
All right, Tim. Awesome. You've set a high bar.
Thank you very much.
Thank you very much. Let's give him a hand. All right, next up is Team Samsung. Minimize power consumption with a novel power ECO flow, to be presented by Jun Seomun.
Okay, hello, my name is Jun, and today I do like to introduce some minimizing power consumption issue flow to save the planet with the low power. Yeah. So the low power is important because once the mobile application is also very important, but in HPC and the database data center, it's also very important for the low power achievement. But so the problem we try to solve is very traditional and hard problem. So during the issue, we can minimize the power by swapping some cells the low power if there are some slacks to be changed. But as you may know, the problem is very complex. So if you change some cells and then the changes affects all other cells in the same timing path, and then that makes the problem very difficult to solve. So that's why we are taking some very easy approach to solve this problem. So while we are trying to minimize the runtime overhead, and then we are trying to minimize the power as much as possible. So here is some equation, but the key is the idea. The key of this idea is that we try to find all the combinations or all candidates for the changing the cells, while it shows some power reduction. But in that case, we did not take care of the other timing impact for this equation. So, and then some changing the cells gives us some better the power reduction, but it affects the a certain amount of the timing slack, and then we did not take that kind of the swapping. So that's we can this problem. We can solve this problem in separate manner, and then we can achieve very high, faster runtime. So here is our overall runtime optimization algorithm. So starting to the Python script, we developed the article, and then we can add some filter mechanism to minimize the runtime. So, and then of course we did not see any timing pass, so we can make this process in parallel. So that's how we can reduce the runtime of this algorithm. So as you can see here, we can use this flow with the current industry solutions. So combined with this kind of the solution, we can achieve the better power reduction, and while we keep the runtime reduction. So here is some example, and then some result of this algorithm. Okay, so in conclusion, during ECO, we can try to minimize the power, but it's very complicated problem. So we try to reduce the problem, and then we try to solve this problem in a realistic runtime. So in conclusion, we can achieve around the 14% of power reduction during this ECO flow. Yeah, that's all.
Thanks so much. Judges, time to pepper with questions.
Oh, I have a question. Actually, sorry. Could you go back? I didn't quite get So what's your approach to optimize the runtime based on what you said, or just put into the more parallel sessions to decide? Sorry, I didn't fully get that part.
This line?
Yeah. So what's the key thing to improve the runtime significantly?
So because once we change some cells to the other cells, it affects the overall timing in the same path, but we ignore that timing impacts, and then we just select all the possible solutions to give us the low power reduction. And then there are some criteria value, the certain coefficient we use, and then if the reduction and the timing effects is smaller than this coefficient, and then we take this solution as our selection. So that means that we can separately calculate the power change and timing change at the same time. So that's why we can make it in parallel. Yeah,
I see. Okay, thank you.
So how do you balance static and dynamic power in your algorithm?
Yeah, we try to both. Yeah.
Yeah, but do you favor one or the other? And if you have a choice, do you do more static or more dynamic?
In this case, we try to focus on the dynamic power. Yeah.
And you find that mostly your changes reduce area or keep it the same? Is that what you...
Yes, we try to keep the same area. Yeah.
Okay.
Yeah.
Any other questions, gentlemen?
So one thing given ECO could be just like you said, right? There's lots of choices, and it's like runtime, a very extensive part, and especially the DRC. That's generally in the advanced node, which I know you from the team, very challenging. Is there anything like, especially on the prediction? Lots of solution choices. Generally, machine learning may come into. So is that also something your group checking, because you generally want to try to really minimize the number of ECOs you want to do, right?
Yes,
at the
right.
last cycle.
But in this case, we did not consider that kind of the approach. Yeah, we just make it simpler. Yeah.
Okay, because it sounds like impact prediction would be a place that you could introduce machine learning.
Yeah, that's possible, but yeah, further work.
All questioned out? All righty. Thank you, Jun. Nice job. Let's give him a round of applause. Next up is our team from Synopsys, Design Timing Effects of Layer-to-Layer Interconnect Skew. This will be presented by Ayhan Mutlu. Did I pronounce that reasonably close?
That's cool.
Okay.
Okay, so yeah, I'm going to be talking about our team's work. Recently, we have basically looked at the possible layer-to-layer skew impact on design's timing. So very quickly, let me tell you what it is. Basically, the timing paths can contain multiple metal layers. And when we, in general, when the users or when the designers are looking at the SPEF corners or parasitic corners, those corners are generated by skewing certain metal parameters to their extremes. So Cmax, Cmin, RCmax, RCmin, etc. So the problem is that may not give you the worst case when it comes to sign-off or when it comes to timing. So pushing everything to minimum doesn't necessarily mean that you're going to get your worst timing. So the problem, what happens during the manufacturing if the metal layers, when they are being manufactured, what happens? There's a mistracking between width and thickness on one layer to the other. So how do we account for that? This is essentially the summary or the main thing that we are trying to address here. So on the right-hand side, we have, let's say, a timing path that's covering or going through two metal layers, metal 3 and metal 4 mainly, right? So if metal 3 and metal 4, R and C goes in different directions, we have 2 to the power 2, 4 combinations. So we analyze those 4 combinations and give you the worst slack. If your timing path has 3 metal layers or 4 metal layers, then we, for 4 metal layers, 2 to the power of 4, so 16 combinations that we analyze. That's enumeration mode, that's what we call it. And then we give you the worst slack. So that is essentially what interconnect skew analysis does. And let me give you a little more detail. So you have your timing paths selected. We take those paths and we model the timing of those paths as a function of per layer resistance and capacitance, and use that information to do either enumeration or Monte Carlo sampling. And in terms of runtime, the overhead is about on average 20% of the overall timing report. So it's not going to impact too much in terms of the overall TAT. But in the end, what you see is if you look at the Gaussian or the slack shift curve, the area that's kind of highlighted with an elliptical is essentially you get the most slack shift when you consider this effect. So those paths need to be fixed. So when you fix those paths, you're essentially making your design more robust towards possible layer-to-layer mistracking during manufacturing. So that's essentially the methodology. And here's an example, an ARM core. So what we are doing, these figures require some explanation. What we are doing here is, if you look at the legend, we are comparing delta slack. So the reference corner is TT. So Cmin versus TT, Cmax versus TT, RCmax. So all the corners around TT, we are looking at the delta slack. And in the end, the purple one is the skew versus TT. So that's essentially the interconnect skew analysis. And if you look at the left-hand side, let's say Cmax is used for setup. This delta slack shift that you get due to mistracking is actually more than even the Cmax that you see in for the setup. And similar idea is applied to hold. Of course, hold is much more important. And we have users using this for hold right now, right? So we want to make sure that we don't have any timing issues, especially in hold, due to this physical phenomena. And since we are modeling the timing of the path or path slack as a function of per layer R and C, we can actually see how the layers are impacting the overall path collection we have. In this case, we have about 100,000 paths, and we are looking at the graphs. On the left side, you have the setup, and on the right side, you have the hold, and which metal layer is dominating the path or the timing of these paths. You can see metal 3 and metal 4 are clearly standing up. So Finally, the analysis, again, is improving design robustness. So what you get in the end is handful of paths compared to what you do in ECO. And fix those paths, make your design more robust, with respect to interconnect or layer-to-layer metal skew or metal mistracking, and then just, continue with the tape out. And with the current methodologies, either, corner or derate, they actually fail to capture this, or if you try to apply a timing derate, of course, you're going to get overly pessimistic results. And here in the figure here, what we are showing here is essentially the usage of this technique. So you have the RC corners, you have 5 RC corners. You see the cubes. For example, you can run this analysis at C-best corner. If you look at the cube at the C-best, so that's at hold analysis, you're essentially skewing the R and C at C-best. Of course, you cannot go beyond C-best. And then that's your total corner, or total RC corner. That gives you you're going to get the impact of that R and C skew by analyzing the timing of that in those cube points, or the black cube points. So that's pretty much what we do.
Well done. You had more time, actually, if you needed it. But now you can take a deep breath and prepare for questions. Friends, Romans, judges.
Hi, so I have two questions. So one is, of course, actually even one of your charts showed, right? Like layers now also even much more, right? Like
right.
We could go 10 layers, 16 layers, and you never know, it could be 20, right? It's it's possible. So when you say like there's 4 layers to the power 4, right? So when you have those many layers, and right now the interconnect is also much longer, you could have a very different segment, and there are also like VS, stacking VS,
correct,
double cut, those things. So then the complexity indeed will go up quite quickly, right?
Correct.
So just, first question is how do you potentially address that? And the second is, so this analysis, like what kind of optimization that you do to really fix this? Like, because, one thing is just like clock, like traditional clock look skew because clock is very nice design, right? But of course, if you do that on the data path, that'll be huge overhead, right?
Correct.
So so those two.
Yeah. So the first question, you're right. 4 layers, 5 layers. You can have 10 layers to the power 10. That's prohibitive, right? So what you have to do is we maybe we can identify the dominating ones. This is again we are giving you a methodology to improve the robustness. We are not saying that this is like sign-off. Just fix these and have it more robust. You're still going to have to do your regular sign-off. You can filter out layers, or you can, because filtering out layers, you can end up maybe 5 dominating layers or something like that. And we have Monte Carlo methodologies or other sampling techniques to essentially to improve the runtime. So that's first. And in terms of ECO, right now what we have is essentially timing ECO. We are just doing timing ECO to fix this and to add some slack margin and stuff like that.
So your layer methodology, I think it makes a lot of sense that M3 and M4 would be the dominant ones because they're running a bulk of interconnects and they're not double thickness and so on. How do you envisage what might happen in the future where you had multiple layers that were like that, or where you had a 3D type design where you had stacked alternating layers of devices and metal? What would happen then?
Good question. Well, it's again, it's multiple layers, and just the challenge we are having right now is basically selecting those paths, because this is a path-based analysis. So selecting those paths that would essentially, be timing critical in the presence of some kind of metal mistracking. So in the future, for example, for those cases you're mentioning, of course, if you have paths going from die to die, and those situations, and of course, those are going to be requiring some pessimistic analysis beforehand, and we have a GBA methodology. That's because we can't just feed in PBA and ask them, this is all you have. So that's probably one thing that we might focus on. Of course, GBA is pessimistic. We have to reduce pessimism because you pick the paths based on the GBA. If your GBA gives you, more paths, then you're going to have to analyze. So the challenge is you have to do a very precise analysis, and while doing that, you have to find the right set of paths that will be impacted from this. So.
What happens if there's correlation? You're assuming independence effectively.
We are
between
actually
layers,
we do have correlation as well. So layer to layer is usually independent, but now we are getting some correlation matrix support. You can have correlation or partial correlation on layer to layer.
This seems like a problem that does lend itself to ML in terms of the selection. Is that something you're looking at, or?
Yeah, that's also in our future plan. Yeah.
See you back here tomorrow. Thank you so much for your participation and your attendance.